think I figured this out. Okay, so I have this PowerPoint to help us review, and we're going to go over each of the reasoning targets. As we do, I will probably be dragging my little image around the screen in the video. I don't know if that will impact the people who are live. If you're watching the video, you shouldn't have any problems. If you are live right now, make sure that you can see my shared screen. If it's not just appearing automatically, it could be in a separate window. I had that happen to me yesterday, and it took me a minute to find it. Okay, also, as we're going, if you're live, feel free to jump in and interrupt me. If you have a question, that is fine. You can also write your questions down to ask at the end, or you can type them into the chat, and I won't be following along in chat, but Sarah will have her chat open, and she can either address that in the chat, or she can interrupt me and I can address the question. Okay, so what we are going to cover today includes magnetism, minerals, rocks, and geologic time. Now, the other thing that we did do in class was plate tectonics, and we talked about plate boundaries. We're going to go ahead and wait on that and assess it on the next unit when we talk about volcanoes and earthquakes, because they're all really related. And that's what's coming. And let's just jump right in. So, first reasoning target, I can explain the presence of and shape of the Earth's magnetic field. I can sketch its shape from the perspective of an observer in outer space. So take a second just to yourself and see if you can remember or have any idea what the Earth's magnetic field looks like, especially if you were to just zoom way out, so an observer from outer space. And I will begin to sketch my interpretation of that right here. That's my Earth, a little lopsided. And I'm going to start drawing in some magnetic field lines. And what you should see is that they're sort of all bunched up over on the left side, and on the right side they're sort of elongated. Take a second and see if you can just sort of remember why that is, what's doing that. So this would be the solar wind. So the sun in my image would be somewhere way over here, and it is constantly emitting particles and charged particles and this thing that we call the solar wind, and the Earth's magnetic field interacts with that, and it makes it so that it's all smushed up on the side facing the sun and elongated on the opposite side. So Sarah, do you have anything to add about the Earth's magnetic field from this perspective?
No, I think that looks good. You have the, of course, like when you kind of like zoom in really close to the Earth, that's where you would just be seeing like the near field version, where it looks much more just like those inner loops, right? But this is a great picture from like the outside, showing that magneto tail stretched out on the side away from the sun.
Exactly, exactly. So that brings us to our near field magnetic field, which is going to come up over here. So the next reasoning target asks you to determine the magnetic inclination of Earth's field for various locations on Earth's surface. And this star is just representing a location that you might be asked to determine the magnetic inclination for. Now, anytime you're asked anything about magnetic inclination on Earth, the first thing you're going to want to do is make a sketch to guide you. So I'm going to go ahead and sketch in the near field magnetic designation just to help me remember it, which is going to help me answer this problem. So it's a little lopsided, and if I was asked to draw it in, I might want to draw multiple examples, but it looks a lot like this near the surface of the Earth. And you need to add some directionality here if you're going to figure out inclination. So Now I have something to guide me as I try to figure out the magnetic inclination of this star down here near the South Pole. And what I'm going to do, I'm going to pretend to just be an observer standing there. Maybe there's a tree, there's an observer. And to that person standing at the South Pole, it would appear that magnetic inclination is pointed in the up direction, right? So vertically up. If you were to move around the Earth, maybe get closer to the equator, then you are going to have something that's much closer to horizontal, right? So vertical at the poles and horizontal at the equator. Now this isn't quite on the equator, so I don't want to draw exactly a horizontal line. However, I do want to make sure it's pointing in the right direction, up or down. So since we're still in the southern hemisphere, I am going to have this next one. That might not be quite horizontal enough. I'm actually going to redo that. All right, we'll try again. So, oops, this is for the second star. And it should be pointing sort of towards the north, right? It always points north, but this is in the sort of vertical dimension. So it's pointing up because it's in the southern hemisphere and near horizontal because we're near the equator. As you move farther northward, in the northern hemisphere, magnetic inclination points downward. And so when you're very near the pole, you're going to be very close to vertical. Okay, so these three arrows would be the magnetic inclination that you would see at these three locations. And again, I'm just basing that on the latitude and what I know about the magnetic field. And I know that it always points up out of the ground in the southern hemisphere and down into the ground in the northern hemisphere. It's more vertical near the poles and more horizontal near the equator. Okay, next reasoning target, I can explain the behavior of magnetic materials given an applied magnetic field. So the whole point of this is just to recognize that magnetic materials are going to align with whatever external field there is. So this is actually why a compass works. It has magnetic minerals, magnetic materials, and they align with the existing magnetic field of the Earth. It's as simple as that. What do magnetic materials do? They align with an external field. In geology, the field that we're talking about is going to be the Earth's field. And while there's lots of different rocks that can keep track of the magnetic field, the most common one that we're going to be talking about are the igneous rocks. And we'll get into that a little more later. Reasoning target, I can define minerals, explain how they are most commonly formed, and provide examples of mineral properties. So we'll start with that definition. Take a second and see if you can remember the formal definition of a mineral. It should be 5 things. I'll wait a second to give you time to think about it. Okay, hopefully you got at least some of these. So a mineral is a naturally occurring inorganic solid with a definite chemical composition and an ordered atomic structure. I'm just going to say it again. Naturally occurring, inorganic, solid, the definite chemical composition, and an ordered atomic structure, right? That definite chemical composition part means that you can write a chemical formula for it, and the ordered atomic structure is what makes it crystalline, right? How do minerals form? There's 2 primary ways that minerals form. You can either have them precipitate out of a solution. This is how, say, calcite or halite form, right? So halite is just salt, and salt is dissolvable in water. And if that water evaporates, the salt is left behind, and we call that precipitating out. When it goes from being dissolved to being a solid, that's the precipitation part. So one way that minerals form is that they precipitate from solution. That's kind of one of our sedimentary processes. Another way that minerals can form is that they can solidify from magma, right? So you have magma, it's hot. As it cools down, what it forms is minerals, and these minerals make up the igneous rocks, right? And so the most common type of mineral that forms in that second way are the silicates, right? So they are found in the igneous rocks, and yeah, those are the two ways. You can either precipitate from solution or solidify from magma. So next up, we have a few of the mineral properties. The first one is cleavage. So that just refers to those through-going planes of weakness in the mineral. So if you went to break it, the mineral is going to preferentially break along these weak plates where you have really weak atomic bonding, and then places where the atomic bonds are much stronger are going to hold together. And so oftentimes you break a mineral and it will break into a characteristic shape. Oftentimes it's habit, which is another mineral property. But the fact that it always breaks into the same shape is because it's breaking along those through-going planes of weakness. Now I mentioned habit, that's another mineral property that refers to the ideal shape of a mineral. Minerals can only take on their ideal habit if they have the time and the space to grow. Another example of a property of a mineral is streak. So streak is the color of the powder that's left behind on unglazed porcelain. If you were to take your mineral and try to sort of write on some porcelain with it. And hardness, this one is really easy to get confused because it doesn't actually mean anything to do with hard. It has to do with scratching resistance. So hardness is the scratching resistance of a mineral. Some minerals are really soft. You can scratch them with your fingernails. And others, like diamond, are really hard and you can't really scratch them with anything. Okay.
So yeah, take a moment and see if there's any questions or if anyone needs a little bit of time to think over anything before we go on. I just want to make sure you all have time to process and ask questions if you need to.
Are you guys looking at notes?
Yes. Are you not seeing them?
No, I am. I was wondering if like there were notes on the computer I could take notes on.
No, I'm not working on any notes.
Okay. I just wanted to make sure because I got on late.
You know, that's fine. That's a good question. Basically, you should just make sure that you can see the screen share that has all of the words and the pictures on it. And you can be taking notes as we go along. You can also take notes afterwards if you rewatch it. And at any time, you can jump in on the chat feature. Is really easy. And then Sarah can either respond to the question or she can interrupt me and I can respond to the question.
Okay, thank you.
Mm-hmm. Or you can also just use your voice and ask a question, obviously. Okay. So that's minerals. Hi, puppy. Hi, puppy. Okay. This is Casper, but we're going to meet him later. Go on. Go back. Okay. I can explain and provide examples of the importance of mineral resources to society. So this question is actually kind of specific, asking you to relate specific mineral properties to specific products. For example, magnetism is a property of minerals, and that's super useful for refrigerator magnets. And I'll just give you one other example to make sure that you can come up with your own examples. I don't want you to just choose mine. But there's a mineral called talc, which is really soft and super absorbent. So it absorbs lots of water. And so that's used in baking powder. So hopefully you can think of a couple of other examples that are not those two examples that you could just give as an example that you know that mineral resources are important to society. This brings us to the rocks. Reasoning target, I can describe the three macro categories of rocks and how each is formed, including the interactions required to change one type of rock into another. So if we start with the three macro categories of rock, hopefully everyone remembers their names: igneous, metamorphic, sedimentary. Sort of brief overarching definitions of each. Igneous rocks cool from magma. Sedimentary rocks are created from other things, either pre-existing rocks or sometimes the pieces of animals or mostly sea creatures, but come from pre-existing things. Metamorphic rocks are rocks that have undergone some sort of change. So that can be a change to their texture. Remember, rock texture refers to the size, shape, and orientation of the mineral grains. And or it could be a change in their composition by switching out certain minerals. So just again, igneous rocks have cooled from magma. Sedimentary rocks are formed from pre-existing things. And metamorphic rocks have undergone some type of change, either to their texture or to their composition. The next part of this talks about going from one rock type into another. So how might you change igneous rock into metamorphic rock? Well, I'm going to go ahead and answer this one sort of in a concept map style, since you will be asked to create your own concept map for the rock cycle. So I'm going to start by thinking about igneous rocks. And if we want to change it into metamorphic, what physically needs to occur in order for this change to happen? Well, we need to raise the temperature and or the pressure. So I'm going to write that down. If you increase the pressure and or the temperature, you can change that igneous rock into a metamorphic rock. A different example would be to change an igneous rock into a sedimentary rock. Well, to do that, you would first have to turn it into sediment and then turn it into sedimentary rock. And you do that by weathering and eroding the original rock, transporting it, depositing it, burying it. We'll go over all of those again when we talk about sedimentary rocks in just 1 second. But generally, those sort of classic sedimentary processes are going to take you from igneous into sedimentary. Now, the next couple I'm going to show up on the screen and give you just a few seconds to think about, but I'm not going to answer them. So if you're not sure how to change the rock into the other rock, make sure that you ask. And you can do that either in the chat now or at the end of the video. First one is, how would you change a sedimentary rock into a metamorphic rock? Sedimentary into igneous. Okay, so those are most, if not all, of the permutations, and hopefully you can figure out how to change each of those into the other. If you can't, definitely ask us that question. But I'm going to leave.
I have a question, Leah.
Yes.
So sedimentary into igneous, does that have to go to metamorphic rock to magma to igneous?
It can go straight from sedimentary to magma.
Okay.
Great question. Anybody else? Okay. All right, so now we're going to go over each of those rock types in turn and talk about the subtypes. So first, I can describe and differentiate between subtypes of igneous rocks based on photographs, descriptions, or hand samples. So igneous rocks, again, cool from magma. The two subtypes are volcanic and plutonic. Difference being, volcanic rocks are rocks that have cooled at or near the surface. So generally speaking, they have erupted Okay, they've erupted from a volcano. That creates volcanic rocks. The other option, the plutonic rocks, these, actually hold on 1 second. See if you remember what plutonic rocks. I'll be right back. Okay, hopefully you remembered plutonic rocks cool underground. So this creates a major difference when you're actually looking at the hand samples. So the plutonic rocks, because they cool underground, it's very insulated. It takes a lot longer to cool. And so those crystals are going to have time to get much bigger. There's just physically more time for the elements that make up those minerals to migrate through the magma to those crystals and just make them really big. The faster a rock cools, the smaller those crystals. So if we start with this rock over here, we want to know if it's volcanic or plutonic. So each color that we're seeing here, these are different crystals. There's these big black ones, and I think there might actually be 2 of the light colored ones, sort of a grayer one and a whiter one. But we can see those differences. We can see those pretty clearly. And so because we can see them with the naked eye, we consider them to be large, coarse crystals. And that means that this rock cooled underground, it is plutonic. We move over here. This has an incredibly different texture. Not only can we not see the crystals with our naked eyes, this one actually has all these little air bubbles in it, right? That's called vesicular. But the thing that's most important is that we can't see individual crystals with the naked eye. And so we know this one must be volcanic. It must have cooled really fast at the surface. This one over here, again, we have different colors of crystals that we can identify. They're pretty big because we can see them when we call them big. And so this is another example of a plutonic rock. It must have cooled underground and had time for these large crystals to grow. Now, the other thing that we talked about with igneous rocks was the color, right? The lighter colors and the pinker colors meant more silica, and the darker colors meant less silica. Now, we're not going to assess on color on these assessments, but that is going to come up when we talk about volcanism because it has huge implications for volcanoes. So don't worry about color for this week, but don't forget it because it will be coming up in the future.
Yeah, do they need to worry about scale at all on pictures like that? Like when we're looking at grains and stuff, or is it as long as you can kind of see the crystal grains, it's large enough, or are we assuming they're kind of similar scale pictures?
Yeah, so all the pictures that I'm using, none of them were taken with a microscope. So in general, most of them are about this big to this big. So you don't really need to worry about scale. It's only if I showed something that was microscopic that we'd have to worry about that.
Okay, thanks.
Mm-hmm. Any other questions? Okay. That brings us to metamorphic rocks. I can describe and differentiate between subtypes of metamorphic rocks based on photographs, descriptions, or hand samples. Oops, that wasn't, there we go. So metamorphic rocks have 2 major subtypes. Well, the major subtypes that we've talked about are contact and regional. Take a second to see if you can remember how each of those is formed. So contact metamorphism happens when rock comes into close contact with magma, right? So on the image here, we have contact where we have volcanoes and magma, right? So that's causing contact metamorphism. And the other type that's super common is regional, and this happens to the due to the intense stresses and pressures of plate tectonics. Again, we're not testing on plate tectonics this time, but it's due to those forces and at those plate boundaries that these types of rocks are created. Now, if we wanted to try to identify in a hand sample tell the difference. The only one of these that we can really easily identify by sight is the regional metamorphism, and only if it has resulted in foliation, right? So foliation refers to the banding of the mineral grains that can happen when you have a preferred direction of stress. So in the non-foliated rock, it has all of these minerals, but they're just sort of randomly aligned inside of the rock. And then the rock is submitted to some intense pressures, which is going to cause the mineral grains to sort of realign and lead to this banding that we call foliation. Here's another example of a rock with foliation. You can see that it's got actually wavy bands. That's super common for a metamorphic rock. And we know based on the direction of the foliation what the pressure would have had to be when this rock formed. It would have had to be from up and down as it's sitting there. But if we were to put it in the picture that we have on the left, right, it's going to go into the regional area, but we'd have to flip it so that the direction of maximum stress is perpendicular to that foliation direction. The final category of rock is sedimentary. So again, we have to describe and differentiate between subtypes. So this one has the most subtypes that we've talked about. We've got clastic, chemical, biochemical, and organic. So we'll go over each of those one at a time. The clastic rocks are the ones that we have that long list of processes that happen to them. So you start with a pre-existing rock and you have to weather it. That means you break down the pre-existing rock, erode it, you remove those little pieces from the parent rock, the original rock. You transport them. Transportation can happen via wind, water, glaciers. These days it can happen on boots or whatever. So you transport it, and then those little grains need to be deposited somewhere. And after they are deposited, they have to be buried. That increases the pressures and the temperatures just a little bit to enable lithification to happen. Lithification is just the fancy word that we use to encompass the complex sort of chemical reactions that are happening that cement that rock together. So that's the clastic rock. Weathering, erosion, transportation, deposition, burial, and lithification. Clastic. Next we have chemical. So chemical rocks form in exactly the same way that certain minerals do, by precipitating from solution. There's not really any difference. The main thing differentiating a chemical rock from that type of mineral is just the size of the sample. So chemical rocks are formed by precipitating from a solution, which again, that's just when, say, for example, the water evaporates and leaves the salt behind. Next, we have biochemical. Now, these ones are created from the hard parts of organisms. So, for example, sea creatures, a lot of them sort of secrete minerals to form a shell. And when they die, that shell still exists and it can get incorporated into the rocks. So that's an example of a biochemical rock. Organic, these are the only rocks that are, these are the only sedimentary rocks that aren't really formed from what we would usually consider minerals, because these ones are formed from the soft parts of living creatures, which primarily we're talking about plants, right? So for example, coal is formed from plant matter, is what it was originally. So the organic one is the soft parts of organisms, biochemical is the hard parts, plastic is from pre-existing rocks, and chemical is precipitated from solutions, usually water. So if we look at each of these rocks, let's see if we can figure out which subtype they are. Starting with this one, we see that it looks kind of shiny, kind of crystally. It's all the same. It's got a lot of texture to it, but it all looks like the same mineral to me. So this is actually a salt, and so that means that its subtype is chemical. This is a chemical sedimentary rock. If we move over here, you can see what look actually like broken up bits of rock, right? These are kind of like, not pebbles, because pebbles are smooth, but like a pebble. And then they're cemented together with this sort of cementy stuff. So this is actually an example of a clastic sedimentary rock. This next one. So this is interesting because you can see that it has all these lines, but this is not foliation. So this is an important point. Both metamorphic rocks and sedimentary rocks can have banding in them, right? But for very different reasons. Sedimentary rocks are created in these horizontal layers, and sometimes the next layer is a different color. So that's what's creating the banding here. One way to tell the difference is that in a sedimentary rock, these are much more likely to be straight lines than sort of curvy lines, right? The metamorphic rocks, a lot of times those lines would be curvy, but not always. Another difference is that sedimentary rocks, when you look at them, they should just look like they're easier to break. They're less crystalline. So if you compare this rock to this one here, hopefully this just looks sort of more crystalline to you, and this looks like maybe if you whacked it really hard, you could break it. The other thing about this rock is, to me at least, it looks like these are a bunch of little sand grains. Okay, and they basically are. This is a sandstone, which makes it another clastic sedimentary rock. So we actually have two examples of clastic sedimentary rocks here. Sandstone, and this one's actually called a breccia, but you don't need to know that name. Okay, that just leaves one to think about. This guy over here. And it's got these really weird sort of markings in it that just repeat and repeat and repeat. Anytime you see something like that, you're probably looking at a fossil. And anytime you're looking at a fossil, you're looking at a biochemical rock. So this is actually a type of limestone. Yeah, it's a type of limestone, and it's biochemical. And if I wasn't sure about that, if I had some hydrochloric acid and I tried to drop it onto this rock, it would react, because sedimentary rocks that are biochemical, they're made from seashells, and seashells have calcite in them, and calcite is a mineral that reacts with hydrochloric acid. Okay. Any questions on rocks so far? So one other thing that we have to talk about with the rocks is explaining why/how igneous rocks are able to record Earth's magnetic field. Okay, so in this image, these lines are meant to represent Earth's field. So we're just zoomed into a single point on the Earth right now. And this is the inclination of Earth's field, right? So just to remind ourselves, it's pointed down, so that we must be somewhere in the northern hemisphere. And these images are attempting to show what happens when a magma cools down into a rock. So when the magma is really hot, you get all of these little magnetic inclinations beginning to appear, but they're all randomly aligned, right? They're not pointing in any one direction. And as the rock cools down and solidifies, all that magnetism aligns with Earth's magnetism, right? So the magnetic signature of the rock is going to align itself parallel to the Earth's magnetic field. And that can only happen while the rock is cooling down. Once it's all cooled down and it's all solid, this magnetism is locked into those mineral grains. Those mineral grains can't move around at all. And that means that the rock is basically a record of the magnetic field of the Earth at the location where it was formed at the time where it was formed. And that's why we can use igneous rocks to tell us something about the past magnetic field of the Earth. So I can identify the hemisphere and approximate latitude of rock formation based on magnetic inclination. Okay. Well, like I said before, anytime we're about to be asked anything about magnetic inclination, we should probably just sketch ourselves a little planet Earth and sketch in the Earth's magnetic field, just approximately, just to remind us how it works. Okay, now we're ready to answer some questions. So we found a rock, and its magnetic inclination is like this. It's pointing up, so that tells us which hemisphere. Can you think which hemisphere, north or south? If you thought south, great job. Anytime that the magnetic field points up, that is southern hemisphere. And now was this one closer to the equator or closer to the poles? Well, it looks fairly vertical to me. So maybe it was formed anywhere in here. Sort of closer to the pole than to the equator at that latitude. We don't know exactly where at that latitude, but somewhere in there. Here's one. It's so in each of these we're assuming that up is up. So this one's horizontal from the perspective of an observer. That means that the rock must have formed near the equator, somewhere in there, for that second one. And then we have one pointing vertically downward, and hopefully you can figure out that one must have formed magnetic North Pole, because that's where you have that magnetism. Okay, we're actually nearing the end now. We started talking about geologic time. So I can utilize the principles of relative dating to place strata into the order they were formed. Let's focus on that first. Beginning with the principles of relative dating. There are quite a few. So we have the principle of inclusions, which states, so remember an inclusion is a little bit of rock inside of a larger rock, right? And the principle of inclusions tells us that the inclusion has to be older than the rock that it's found in. We have the principle of cross-cutting relationships. So that tells us that any feature that cuts another rock has to be younger than the rock that it's cutting. Normally, what you're going to see when you're going to be able to use that is when you're looking at igneous intrusions and when you're looking at faults. So, principle of inclusions, principle of cross-cutting relationships, principle of original horizontality. So, if you see a sedimentary rock, all sedimentary rocks are first formed horizontal. If you see it in any other position, then that must have happened after it was formed. Especially if you see it all wavy and scrunched. That has to happen after the rock was originally formed. Then we have principle of superposition, which means that the one on the bottom, again, we're talking about sedimentary rocks, and the sedimentary rock on the bottom has to be older than the sedimentary rock on the top. And we have the principle of lateral continuity, which tells us that rocks don't just stop, right? They sort of keep going. They're laterally continuous until they hit like the edge of the basin or something. They don't just stop, okay? So using those principles, we ought to be able to place strata into the order they were formed. Strata just means rock layers. So here's one example. Take a second and see if you can think through the order of which these rocks were created. Hopefully. You said that C is the oldest. How do I know that? Principle of inclusion. So why my pen's not working. Okay, so those little inclusions that you can see, there's little bits of rock C inside of rock A, and that's an inclusion. So that tells us that C has to be older than A. The next oldest would be A. I know that because A is actually an igneous intrusion. I know it's an igneous intrusion because its edges are all sort of blobby, right? So that's what I would expect from an igneous intrusion. Also, if you see those little stars on the outside of the intrusion, some images have that, some don't. But it's just pointing out the fact that along that margin, you'd actually expect contact metamorphism. I know that that's older than B because B is cutting through it, right? It's going straight through. So B is probably a different type of magma that came later. Okay. So next we have this one. I'll give you a little bit longer to see if you can think through the order here. Okay, so we'll start from oldest and we'll go to youngest. So it looks like B is the youngest, right? And I know that because the principle of superposition, B is on the bottom, followed by C, followed by D. Those are all sedimentary layers that would have originally been horizontal. Now, after D, it's a little tricky to know if A or M is the next thing. However, M, if you look really closely, is actually cutting A, right? So there's a little piece of A that's sort of right there, sort of under E at the corner with M. So A is cut by M, so principle of cross-cutting relationships, A has to be older than M. After that, well, it looks like these rocks were buried and folded and then uplifted, and new sedimentary layers were put down on top of them. So that's how we get to E. Now there is an unconformity there, where you have sedimentary layer on the bottom coming up at an angle to another sedimentary layer. So that's actually an angular unconformity. We'll talk about more in a second. So we have layer E, layer F, layer G, another unconformity. It's again an angular unconformity, and then H. Okay. So let's go ahead and talk about these unconformities in a little more detail. And it looks like my highlighters come back. Give me second, here, while I try to figure this out, you can think about what unconformity this is. This is meant to be a single smooth line. Here, maybe I'll redo it. Showing you the unconformity itself. And we do have sedimentary rocks coming at an angle to other sedimentary rocks. So that is an angular unconformity. Different type of unconformity is called a disconformity. This happens when you have sedimentary layers on the bottom and sedimentary layers on the top, and they're not at an angle with one another. So hopefully you can tell. And I've lost my laser pointer again. But hopefully you can tell where the unconformity is. And again, disconformity, sedimentary layers on sedimentary layers. This just means that you had some time where sedimentation was not happening, maybe erosion was happening, and some layers got removed, but then new sedimentary layers started being added again without any sort of folding or anything else like that. This one, take a second and see if you can figure out what this one is. So this is a little hard to tell, but this is another angular unconformity where you have sedimentary layers coming at an angle to other sedimentary layers. And then finally, we have a nonconformity. Nonconformities are the final kind. They happen when you have igneous or metamorphic rocks on the bottom, because in general, specifically you have plutonic igneous rocks on the bottom, because both plutonic igneous rocks and metamorphic rocks are created much deeper down in the crust, right? So if you see those with sedimentary rocks right on top, you know that you have eroded a lot of material to bring those deep rocks up to the surface where sedimentary rocks can form on them. So unconformities in every instance represent missing time when no new sediment, no new rock was being created in that location. 3 different types: angular, where sedimentary layers come up at an angle to other sedimentary rocks; disconformity, where sedimentary rock layers are on top of other sedimentary rock layers, but there was a period of non-deposition; and nonconformity, where you have the plutonic igneous or the metamorphic rocks on the bottom and the sedimentary rocks on the top. Okay, final reasoning target. I can place important events in Earth history onto a timeline of Earth history. So if we start at the beginning, we actually have the Hadean era, when Earth forms, our first crust forms, the Earth gets its moon. This period is when we had extensive volcanism occurring on the planet. This was followed by the Archean, when we have our first single-celled organisms, and they begin to oxygenate the atmosphere. The early atmosphere was very, very different than today's oxygen-rich atmosphere. This is followed by the Proterozoic, which is sort of the very earliest life. It was all in the oceans. We didn't have an ozone layer yet, so there wasn't life on land. But we did start to have things like jellyfish, corals, and clams. And all of these represent the Precambrian. So something like 80–88% of Earth history is these 3 eons. The 4th eon, the one that we are in today actually, is the Phanerozoic. And this one we break down into 3 eras: Paleozoic, Mesozoic, Cenozoic. The Paleozoic, we call the age of the fishes, right? So this is when we have a real just diversification of life in the oceans. We have lots of different creatures coexisting for the first time. And after this, we have a mass extinction event, and then we have the Mesozoic. In the Mesozoic, this is known as the age of reptiles. This is when the dinosaurs lived, but it ends with another mass extinction, which brings us to the Cenozoic, the age of mammals, which is also the age that we are currently still in. Okay, that's it for the slideshow. Does anyone have any more questions?
I have a question about our test that will go live on Wednesday. So how much time are you permitting for the test?
Good question. I don't have the exact answer for you right now, so I don't want to give you a number, but it's not short. Sarah, do you have something more that you feel like? It'll be based on the final number of questions.
You'll also be you'll be able to take them in the different portions at different times, right? So all the different portions will be open to you. So like you can come in, because it's online, because it's this different format, you can decide, oh, I'm going to take the essay now, and then, you know, later on you can take the exam questions. You're going to have a lot more flexibility in terms of when you can take the different pieces. You do not have to do the whole thing in one setting. So maybe that helps some.
So from what I'm understanding, we have a time frame for each section. It's not one whole time frame for the whole test. You just have to finish it by Friday.
Right. And a few of the sections are actually untimed. So like the essay questions, I mean, really in those cases, you're just like getting the assignment and completing it and submitting it by Friday like you would something. It's not a timed option kind of thing. The timed ones will be, I don't have the whole list in front of me. I don't know if you remember off the top of your head, Leah, but the exam question-y portion will be timed, and then I think there was some other segment that was timed, but
yeah,
we could probably send out or post details on those, but they'll also be, you know, I mean, when they're live, it'll be really obvious, and we're trying to make sure that they shouldn't take you the full time that we're allotting, really, for the timed portions. We're trying to be kind of generous with that. So, you know, like, don't look at it and be like, oh my gosh, it's going to take 8 hours or something. I don't think they're that long, but,
no.
but we didn't want to make them too short, but they're also not so long that you can, I don't know, learn all of geology in a day and try to do them then.
And we can be more explicit about what exactly the timing is and which ones have time limits. We can post an announcement about that either late Tuesday or early on Wednesday.
And I may have missed this in your email. Are we taking it on ACE or on a different website?
On ACE.
Okay.
I'm gonna stop my screen share. Now I can see everyone.
Did you want to stop recording or?
I don't know.
Recording for now.
I was going to get my dogs in here. I thought maybe I'd record that too. I don't know if anyone wants to meet my dogs, but my dogs, they were already trying to wander in earlier, so I thought I would just introduce them. I'm gonna go grab them.
Let's see if I can get mine to come over, but I'm not sure if he will. He doesn't like coming to this part of the room. Shadow. Oh, you heard me. Come here.
Good boy. dog Buddy barks too much. He's sleeping. He was sleeping.
So fluffy.
Yes, he's a doodle. He's a mini golden doodle. Kind of looks like an old man sometimes. What are you doing? He was all about coming to join us earlier. Ginger, you want to come look at his parrot? All right, Ginger. Okay, we'll do that. I'm sorry.
Dogs don't cooperate. Let's see if mine will. Shadow. Here's mine.
Ginger.
That's as good as he's gonna do.
Ginger's older. He just likes pets. Okay. Those are my. You will probably see them in some of the videos that we will be making. Okay, should I turn off the video? Recording.
Got all our major questions done.